Hey there, my name is Henry. Today, we're going to dive into the fascinating world of advanced machining techniques. Buckle up because we're about to explore about computer numerical control machining, electrical discharge machining, and the futuristic bioprinting, which is also 3D printing. Now, let's get started. First up, CNC machining. Imagine a sculpture, but instead of a chisel, they use a computer-controlled machine. CNC machining is a manufacturing method that automates the control, movement, and precision of the machine tools through the use of pre-programmed computer software. This process can control a range of complex machinery, from grinders and lathes to mills and rotors. With CNC machining, 3-axis or even 5-axis, cutting tasks, all these tasks can be accomplished in a single set of prompts. So how does CNC work? Well, engineers or designers start by creating a digital model using CAD software. The CAD design is imported into the CAM software, which translates the design to the G-code, the machine language used by CNC machines. Next, the raw material, or also known as the workpiece, is secured to the CNC machine. The appropriate tools are selected and installed in the machine. The machine follows the G-code instructions, moving its tools in precise motions to remove materials from the workpiece. The process includes operations such as drilling, milling, turning, and grinding. After the primary machining is complete, additional processes like deburring, polishing, and surface finishing may be performed to achieve the desired specifications and quality. The beauty in CNC is its precision and versatility. From automotive parts to intricate jewelry, CNC can handle it all. Next, let's spark up some interest with EDM. No, not that electrical dance music. It's electrical discharge machining. Think of EDM as a precise controlled lightning. Is it this kind of lightning? No. It is actually electrical discharges, or also known as sparks, that are used to erode materials, allowing for creation of incredibly detailed and complex shapes. The temperature achieved at the point of spark in EDM can be significantly higher than the surface of the temperature of the sun. This is exactly why EDM is highly versatile and can cut a wide range of materials, particularly those that are difficult to machine using conventional methods. The EDM process starts off by having the workpiece and electrode being submerged in a dielectric fluid, where the power supply unit is connected to the electrode and the workpiece. Then a voltage is applied between the workpiece and the electrode. When the electrode approaches the workpiece, the dielectric fluid breaks down and a spark is generated across the gap. The spark creates a high-temperature plasma channel that melts and vaporizes a small portion of the workpiece. The molten material is rapidly cooled by the dielectric fluid, causing it to solidify and to be flushed away from the gap. This process is repeated many times per second, gradually removing material from the workpiece and shaping it according to the electrode's geometry. The servo system maintains the precise gap between the electrode and the workpiece. Not only that, the power supply adjusts the energy of the spark control to control the rate of the material removal, and the precision can be as accurate as 0.002 millimeters. The two commonly used types of EDMs are die-sinking EDM and wired EDM. The die-sinking EDM uses a shaped electrode to create complex cavities and shapes in the workpiece, commonly used for mold making and complicated detailed part manufacturing. While as for the wired EDM, it uses a very thin electrically charged wire as the electrode. The wire moves in a programmed path to cut the workpiece, making it suitable for cutting complex shapes and contours. EDM is a game changer for industries like aerospace and medical devices, where precision is non-negotiable. And now, let's leap into the future with bioprinting. This isn't your average 3D printing. We're talking about printing with cells and to create living tissues and organs. Bioprinting is an advanced form of 3D printing that uses bioinks, which are materials composed of living cells, which are used to create complex tissue structures. This technology has broad applications in medical science, including prosthetics and skin grafts, and even extends to the food industry. The bioprinting process begins with cell sourcing. Cells can be harvested from various sources, including patient biopsies, stem cell lines, or donor tissues. These cells are then cultured and expanded in the laboratory to obtain a sufficient quantity for bioprinting. Next, we prepare the bioink. Bioink is a mixture of living cells and biocompatible materials, such as hydrogels, that provide supportive environment for the cells. The bioink must have the right consistency and properties to be printed and support the cell viability. With the bioink ready, the next step is designing a blueprint. Using computer-aided design software, scientists create a detailed 3D model of the tissue or organ to be printed. This model includes the detailed architecture and cellular organization needed for the tissue to function. just like the passageway for the blood to run. Now comes the printing process. The bioprinter deposits the bioink layer by layer according to the digital blueprint. This layer-by-layer approach allows for precise control over the placement of cells and materials, creating complex structures that mimic natural tissues. Once the structure is printed, it is not yet ready for use. The printed tissues need to mature and develop their functionality. This maturation process takes place in bioreactor, which provides a controlled environment for the tissues to grow and develop. Finally, the matured tissues are tested for functionality and structural integrity. They undergo rigorous quality control to ensure that they meet the required specifications before they are being used in the medical applications. Bioprinting has the potential to revolutionize medicine. Imagine being able to print skin for birth victims, or even an entire organ for transplants. Furthermore, we could even eliminate the need to kill animals for food by generating synthetic food through bioprinting. The future is here, and it is bioprinted. So finally, let's compare these amazing technologies. CNC machining is known for its high precision and versatility, working with materials like metals, plastic, and wood to create everything from automotive parts to intricate jewelry. EDM, on the other hand, offers extreme precision, capable of achieving accuracies up to 0.002 millimeters, making it ideal for hard-to-machine metals and applications in mold-making aerospace. Bioprinting stands out with its ability to use bioinks made of living cells to create complex tissue structures, revolutionizing medical prosthetics, skin grafts, and even organ transplants. In conclusion, each of these technologies is revolutionary in its field. CNC machining automates precision manufacturing. EDM allows for intricate designs with hard metals, and bioprinting pushes the boundaries of healthcare and sustainability. That's it for today's dive into CNC, EDM, and bioprinting. I hope you found this video informative. So, until then, stay curious.